Okay, here we are. It's the physics video lecture. Physics 203, video lecture 21. We're talking about Hamilt and Jacobi theory. Last lecture I did a pretty involved derivation of that, and it's not going to be the last time I do that derivation. But I'm going to go ahead and do an application and remind us where we are. And it's a really interesting theory and application, so we're going to do enough repetition on it so that we really know what's going on here. Okay, so what we have is when we started talking about the action as a function of the upper coordinate. So let's go ahead and really briefly. We did this here, integral L dt, and we left this as a function of the upper coordinate, and that gave us an expression for the action as a function of the coordinates and the time. With P sub I equals ds dq sub I. Also, we found ds dt, which we have there explicitly. We take that time derivative, was just Lagrangian, plus h equals 0. Okay, and the combination of these relations here allowed us to set up a differential equation, the Hamilt-Jacobi equation, which was, and I'll write all the arguments here. Okay, so ds dt, that's a function of the coordinates and the time, plus h, function of the coordinates, the derivative with respect to the coordinates. I'm writing it as the full set of them just by writing as a vector. And time is equal to 0. So that was a partial differential equation, and we didn't know what to do with it, but then we figured out what to do with it. So good, that was the Hamilt-Jacobi equation, and I'm just going to write here solve, and what we're going to talk about today is how to solve it. So you solve it to obtain s equals s of the coordinates n constants of alpha 1 through alpha n, and time, the alpha equals, alpha sub 1 to alpha sub n, are integration constants for a partial differential equation of this type. Okay. Next, having obtained the solution, we interpret it as a canonical, as the generating function of a canonical transformation. And what we then find is that, so we've got this thing, okay? We then find the following. As well, what went into it, we of course have P sub I is equal to ds dq sub I. Of course, that went into the construction in the first place. And beta, let's write this down better. Beta sub I equals ds d alpha sub I. Or a set of n algebraic equations because these beta sub I are constants. They're the new coordinates in the problem, but they're constants. The alpha sub I are also constants. So these equations are algebraic if you can, and let's go ahead and write this in as well. Algebraic equations, the beta sub I are constants. So beta sub I equals ds d alpha sub I of q1 to qn, alpha sub 1, alpha sub n, and t. So you have a bunch of algebraic relations now. If you can invert these, then you're lucky. Okay, then you actually have the solution. So invert to obtain q sub I of t. So this is what you end up with, a bunch of algebraic relations. And we're going to just do some examples here because we got to stop talking about generalities and actually do an example. Okay, and then we'll come back to the theory and work our way into the set of a number of different techniques, okay, to deal with that. Good, so our first example is just going to be the linear harmonic oscillator once again. 1 degree of freedom, and then we're of course going to have to move into many degrees of freedom as well. But the harmonic oscillator actually, before I do something there, I should put a note that we had last time. So note, and very important, if energy is conserved, so if H equals constant equals E, then we have ds dt equals minus E. Okay, right? This is a constant, so ds dt partial equals minus E, and then we can write this, S equals S0 of Q minus E times T. We had that before. We're gonna make use of this repeatedly because all of our examples, or most all of our examples, are gonna have conservation of energy. So very important. So the energy conserved case, this is the form of your trial solution. So when you get S, you're going to be solving for S0 and then getting the complete S is S0 minus E times T. Okay, so we're going to do that right away. So good, for the harmonic oscillator, we have P squared over 2M plus 1/2 K. I'll go ahead and use Q. 1/2 K Q squared is equal to E. Okay. This is the Hamiltonian with a constant energy. And since E is equal to constant, this is going to be our only conserved quantity in the problem, and we're going to go ahead and name it alpha. That just seems to be traditional. Okay. So what we're going to have is, so next, find S of Q alpha and T equals S naught minus alpha T. Okay, that's what we're going to do next. Okay, so now what is the Hamilton-Jacobi equation? There's the Hamiltonian. This is what we're trying to look for. Apparently we have 1 over 2m ds naught dq squared, right? That's our p squared over 2m plus 1/2 k q squared is equal to alpha. We're calling our conserved quantity alpha. And okay, this is a differential equation, and it's been reduced to an ordinary differential equation. A differential equation for S naught of Q. So we can do this. So we have ds naught dq squared is equal to 2m alpha. In fact, let's just go ahead and multiply this out like so. So 2m alpha minus kmq squared, because the 2's cancel. So kmq squared or ds naught dq equals plus minus root 2m alpha minus kmq squared. And let's go ahead and formulate S naught like this. We're going to leave it in the form of the integral. So S naught is equal to plus minus integral root 2m alpha minus kmq squared dq. Okay, we can prime everything like that, q prime squared. I put the q up there, don't worry about the lower boundary. And this allows us to write our S of Q alpha and T is equal to this integral here minus alpha times T. 2m alpha minus k m q squared prime dq prime minus alpha t, as advertised right here. We're still going to have to do this integral, but this is legitimate. And now we don't have our rules here. Yeah, we do. We have the rules up here, namely the beta, which is a constant, is ds d alpha. Okay, and the alpha is a constant. In fact, the alpha in here is the one we're talking about there. It's conserved quantity in the problem. So I'm going to leave this as a homework, but I'm going to get started because you'll see this is I'll take it almost to the end. Okay. So what we have to do next, we found our action. So let's go ahead and write here next. This beta, which is a constant, is equal to ds d alpha, partial alpha. So this is actually kind of fun. So we have plus minus integral. We're going to differentiate right under the integral sign we have. That's something to 1/2 power. So we have 1/2 root 2m alpha minus km q prime squared. And the inner derivative, since derivative with respect to alpha is just 2m, and we still have a dq minus t. 2's cancel. Now our goal is to find Q of t. And since this is the linear harmonic oscillator, did I write it down anywhere? Harmonic oscillator? Yeah. Since this is the harmonic oscillator, we know what the answer is going to be, sine or a cosine. So let's see how that will come about. I'll do one more step and then hand it over to you guys. Yeah, you guys will turn this one in, but leave enough space in your notes because it's just going to be a couple more lines so you can fill in your notes as well. But yeah, we have beta plus t. Okay, so we already know what beta is, some constant time apparently. Beta plus t is equal to plus minus this integral here. Now we can simplify, but what you're going to see, let's go ahead and pull an m and a root 2m alpha, root 1 minus km 2m alpha q prime squared, got a dq prime. This needs a little cleaning up, but you clearly are looking at, if you see what you've got here, you're looking at an inverse cosine or sine. Okay. So eventually, this is homework, but we're 90% of the way there. We're going to end up with Q of t is equal to some constant cosine omega t plus phi. Okay. And omega is equal to, of course, root k over m. And in terms of the amplitude, we also know that we're going to have 1/2 k a squared should be alpha, because that was our energy. 1/2 k amplitude squared is the energy. Okay. So yeah, you integrate this. So integrate inverse cosine, etc., and then make sure all your constants come out. And if I made a mistake up there, it'll come out in the wash, right? Because you know that you have to end up with this. But this illustrated an important technique, namely that you can often leave part of your action, part of your solution in integral form, because you're going to come back later and do some differentiation on it anyway. But good, so that is the harmonic oscillator example. And I'm going to do another example now. Also one-dimensional, actually the simplest example. And that is the free particle. In one dimension. So the free particle in one dimension, we know that p squared over 2m is equal to the energy. Okay, that's our Hamiltonian, right? P squared over 2m, because potential energy is 0 or constant. So p squared over 2m equals E. We can therefore write 1 over 2m ds naught dq squared is equal to, we'll go ahead and call E energy alpha again. And now this is differential equation, so ds 0 EQ is equal to plus minus 2m alpha. Got a square root there. Okay. And S naught, let's go ahead. Again, actually, well, I've got room. I should probably label some of these steps for you. So this was the harmonic oscillator. Now, so S naught of Q and alpha is equal to plus minus root 2m alpha Q. And S of Q, alpha, and T is equal to this S naught, so plus minus root 2m alpha. 2m alpha Q. Alpha's under the square root. 2m alpha Q minus alpha times T. Remember, that's that minus E times T. I'm going to go ahead and label this while I'm thinking about it. So this is our Hamiltonian. Equals E equals constant. Right. This is the Hamilton-Jacobi equation. In these next two steps, I'm solving it. Okay. So I'm solving it, and now I've actually arrived at the solution to the Hamilton-Jacobi equation. And now we remember that we have this relation, beta is a constant, is equal to ds d alpha, which is to say beta is equal to this plus minus root 2m, and then I've got the square root of alpha, so that's 1 over 2 square roots of alpha, like that. I'll put parentheses around there, times q, so that was my dsd alpha, but I also had one here, so minus t. Okay. So this is that result that I said, well, if you can invert it, you're golden, right? You can have your q of t, and of course we can see here pretty easily that we've got a q of t. So beta is plus minus. Now this root 2m, let's see what we actually have here. We have a root 2m over 4 alpha, bring that under the square root, q minus t. And since the alpha is the energy, I'll just show us what this is. That's m over 2, but remember the energy is mv squared over 2. So those 2's would cancel, m would cancel. And I'm looking at a 1 over v squared, since that's the square root of both of those. That's 1 over v, okay? 1 over the magnitude of v. So what this result is q is equal to, and by the way, since this is a constant, let's go ahead and call it v naught. Okay. So q is equal to v naught beta plus v naught t. V naught and beta are both constants, so we end up with q equals Q0 plus V0T. Okay, that's the equation of a free particle, straight line. Okay. What about the plus and minus sign? Well, yeah, it's it. In fact, it's we can say the V naught has a, leave it with without the plus or minus. Plus or minus sign is in the V naught. Okay. And since those are the two, two possibilities, that covers the entire range of possibilities. So yeah, we'll go ahead and just leave it like that. Now I'm going to do this problem one more time. How we doing time-wise today? Yeah, we're fine. I'm going to do this problem again because there's another aspect here that actually simplifies things a bit. And that is, erase this, yeah. We know something about these types of systems here that we can make use of. Namely, recall that P is equal to, so P sub I is equal to ds dq sub I. That means that we could have, in this particular case here, since we know P is a constant, right? This is a free particle, it has constant momentum. We can write S naught is simply equal to alpha Q. Where alpha is the conserved momentum. So this time, instead of the conserved energy that we did last time, it's going to be the conserved momentum. So there are more than one way to solve a given problem. And this technique will be really important when we go to multivariable problems. So we'll do it right here. So this would be our S0, and you'll notice we get there a lot faster. So now we have S is equal to alpha Q, right? ds dq is P, and P is the conserved momentum. Now, in terms of, it still has to be minus E times T, but now it's minus alpha squared over 2m times T, right? P squared over 2m is your energy, like over there. So notice this is an alternate form, and good thing I have the other one on the board as well. This is an alternate form of the solution. Here we had root 2m alpha q minus alpha t. Here we have alpha q minus alpha squared over 2m t. Let's go ahead and do this one quickly, see what happens. Yeah, so just keep this right up here. Okay, so now beta equals ds d alpha looks like this. Beta equals ds d alpha, which is q, minus 2 alpha over 2m. Okay. to alpha over 2m times t and q is equal to alpha over mt plus beta. Of course, what's alpha over m? Alpha is a momentum, so that's mv over m. That's just v, right? So here we would get q is equal to v naught t plus beta, just as we had before. But this trick here, we'll call it that, is really crucial in what follows. This is actually one of the strengths of the whole Hamilt-Jacobi method, that we can deal with cyclic variables, which is what we actually were just doing. This is how we deal with cyclic variables. Okay, so the next thing I want to do is talk about multivariable problems. So next, multivariable problems. So at least we've done a couple of basic single variable problems. Okay. Okay, so we're back to the Hamilton-Jacobi equation in its general form. So for n greater than one variable. So let's go ahead and just write down the Hamilton-Jacobi equation of ds dt h of q1 qn ds dq1 ds dqn and t equals 0. So there's the Hamilton-Jacobi equation. That's a q. The question is, how do you solve a partial differential equation of this form? And the answer is separation of variables. And the separation of variables takes on, for us, an unusual form, because you've been doing a lot of separation of variables in electromagnetism and quantum mechanics, and there it's always a product. But separation of variables for this equation is a sum. Separation of variables. And what we're trying to do then is separate S into S sub I, well, I'll just write them out. S sub 1 of Q sub 1 all the way down to S sub n of Q sub n. This is our goal, to separate variables in this form. And if we can do that, then the Hamilton-Jacobi equation will just reduce to some quadratures, and it will be solvable. So separation of variables takes on this form, and I'm going to give an example. So yeah, just important to see this. And the other ingredient, so I'm going to number these here, is the example we just did. If H, or if Q sub I is cyclic in our Hamiltonian. Remember, of course, we're starting with a Hamiltonian. If Q sub I is cyclic, then S sub I can simply be written as alpha sub I Q sub I. Because if Q sub I is cyclic, then alpha sub I is the conserved momentum, and we retain that conserved momentum in the new system of coordinates. Okay. So let me make sure I write that down. Where alpha sub I is the conserved momentum. You can say it's conserved old momentum, but it's also the new momentum. Okay, it's conserved momentum from our Hamiltonian system. Okay. Of our Hamiltonian system. Okay, so what we're going to do is set up what next? Projectile motion, obviously. We've got to do projectile motion, and we're going to end up doing the Kepler problem too. But this is our ansatz here. So next example, projectile motion. And this is also one I'm going to set up and let you guys finish. But let's see, what do we know about projectile motion? First of all, let's let it be in the xy plane, and positive y is up. Okay, so then we know that px squared over 2m plus py squared over 2m plus mgy, that's our Hamiltonian, equals E, and I'm going to even name that E alpha again. It seems to be used a lot. Okay, so there's our Hamiltonian. Okay, the Hamilton-Jacobi equation is just that ds dp plus this is 0, but of course, because energy is conserved, and I've just written that down here, our Hamilton-Jacobi equation is actually, I'll put this right here, let's actually put a period right there. Okay, what we're going to have now, S is going to be Sx of x plus Sy of y minus alpha t. That's what our S is going to end up looking like. Right, that's a separation of variables. And because we have this Hamilton-Jacobi equation, we have ds dx is equal to alpha. So dsx dx is equal to alpha x. Okay, that is from the conserved quantity the way I just did it. So Sx of x alpha x x. Okay. So the Hamilton-Jacobi equation, which is this one, alpha is going to be the E, alpha x is the linear momentum in x direction. So now we have, I'll just write it out. The px is the alpha x, so we got alpha x squared over 2m plus 1 over 2m ds of y dy squared plus mgy is equal to E, which is that alpha. So this now is what we have to solve, and it should be a pretty trivial integration. we have to solve this to get S sub y. And when we have S sub y, we'll have it here. S sub x we already have, alpha t, and then we'll be ready to continue on. So let's do this in a couple of steps, and then I'll leave it for you guys to finish up. So what do we have here? We have 1 over 2m 8s sub y squared alpha minus alpha x squared over 2m minus mdy dsy dy. Different ways to multiply this out. We'll go ahead and do the 2m alpha minus alpha x squared 2m. And sure, we can go ahead and skip that step. Yeah, so once you've done that, S sub y of y is just the integral of this thing. And since we got a square root of something here, the integral will be that same expression to the 3/2 power, and then some constant. I'm just going to write integral, etc. So next, you've got this, okay, because you've integrated that S sub y of y, got that there. This one here, alpha x times x, which showed up here as well. So yeah, you're going to have your alphas and your alpha x's in a couple of places. And then, so you do this, comma, then beta equals, you'll have beta sub x equals d s d alpha sub x, etc. And from those equations, you can then obtain the equations for the parabolic motion, projectile motion. So that too will be homework, although this one I think I'm going to pick up next time. Oops, homework. Pick up next time and run with a bit more. So we want to do this, we want to do the Kepler problem, and at that point we want to actually get a real overview of the method, which we'll get, and then we'll have something good. Okay, so let's leave it at that. See you guys next time.